For our first Hello World program on the PIC, we're going to do something slightly unusual. And bear with me, there are several reasons why I'm doing it this way. We're going to build a 555 timer in astable mode with a really slow clock rate and use that as an external clock for our PIC. We're going to slap an LED on the output of the 555 so we can see the clock pulses, and we're going to program the PIC with a Hello World program which simply flashes an LED. Now, you remember when we were going over the operations of a microprocessor and how it works, there were several steps the microprocessor takes to complete an instruction. Because we are manually providing a clock with a visual indication, we'll be not only able to see the program at work, but we can count the number of steps required for the operations going on inside the microcontroller. So, build up your circuit on your breadboard like I did here. The schematic is in the downloads section. Very important, notice that the maximum operating voltage of the PIC is 5.5 volts. The AA battery pack you got in the analog electronics kit puts out 6 volts. The 9-volt battery, of course, puts out 9 volts. So unless you happen to have a battery holder that holds 2 or 3 AA or AAA batteries, you're going to need to knock down that voltage. Now, you have several options here. You can do the simple thing and simply remove one of the batteries and jump across the leads with a gator clip like I did here. Or you can use your 3.3 volt regulator, which you got in the analog kit, and use that to provide power to your PIC. I'm not including that in the schematic, but you're a trained professional. I know you can figure out how to do that. Or you can put 1 or 2 silicone diodes in series from the battery pack to the power bus on your breadboard. Silicone diodes drop 0.7 volts each, so that knocks down the voltage 0.7 to 1.4 volts, getting the battery pack voltage to within the specs onto your PIC. Depends on how fresh your batteries are. If they're new batteries, your pack might be putting out as high as 7 volts. Or if you happen to be using nickel-cadmium rechargeable AA's in your battery pack, those batteries have a lower output voltage of 1.25 volts each, instead of the normal 1.5 volts. So the total voltage of your pack only comes up to 5 volts, and you won't have a problem with overvoltage. You'll need to wire up your PIC 3 to the breadboard, and you can see what I did here. I just simply plugged in the included jumper right into the breadboard, and then used jumper wires to connect to the correct pins on the PIC. Notice also this PIC uses those connector designations VDD and VSS. So, hearkening back to our MOSFET transistors, that's for the drain and source. So the source was negative and the drain was positive, right? So you'll notice that this PIC chip has also got the negative power connection on the top side and positive on the bottom side. The opposite of most microchips. So be aware of that. Get it all wired up and turn off the battery power. Plug in your PIC to your computer and wait for your computer to register it and install the drivers. Now, I noticed it took an unusually long time, like several minutes. Let it just sit there and chug away until it lets you know it's installed. So once everything is installed, go ahead and fire up MPLAB-X IDE. Now, I'm using version 3.40 for this tutorial. If by the time you follow on in this lesson the version is updated, hopefully not much has changed. If you could just follow along in these steps with me, we'll get you up and running first, and then we'll backtrack and look at everything we did, why we did it, and what it means, okay? So we're going to start by making a new project. So go to File, New Project. A pop-up window will appear, and we need to choose what kind of project, which will be under Microchip Embedded and Standalone Project. If that is highlighted, then click on Next. Now we need to tell it what kind of chip we're going to use. You can leave it on all families if you want, and when you click on the device drop-down menu, you get a huge menu of pretty much all of Microchip's production line. Scroll down the list until you get to the PIC 16F categories, and our chip is the second one there. So keep an eye out for it. PIC 16F 1455, click on it, and then click on Next. In the next window, we have an option for a debug header. which we are actually not going to use. So if it is set to none already, if it is not set to none already, set it to none, and then click on Next. Now it wants to know what kind of programmer we're going to use. Now we have the PIC 3 in our kit, so select that. If by chance you were supplying your own parts and you had a PIC 2, I'm afraid this is where you'll encounter some difficulty. Now it is possible to program the 16F1455 with a PIC 2, but you'll need to do some reprogramming in MPLAB, which is beyond the scope of this lesson. So you're on your own there. Obviously, once you get it set up, you would have to select PIC 2. So for the rest of us, click on PIC 3 and then click Next. Almost done. We now need to tell it what compiler we're going to use. We are going to be doing some raw machine code programming, assembly language. So we're going to use the built-in microchip assembler. Select MPASM and then click on Next. Lastly, we need to tell it where we want to save our project. So pick a spot anywhere you want on your computer's hard drive, but make sure there are no spaces in either the folder name or the project name. I actually have not encountered any problems with spaces and names, but it can happen, and I want to avoid mysterious problems. So you can do like I did and put underscores in the place of spaces, or hyphens if you want. So select the folder you want to save them, and I would recommend making a new folder. Give it a name like pic_programs or something like that. Give your project a name like Blinker, and then click on Finish. Our project is now built, but we need to do some more setup. MPLAB is actually multiple software interfaces all bundled into one window. That's why it's so complicated to set up. So in the upper left window, you can see 3 tabs. If it's not on the Projects tab, then you can select that tab. And in that list, you'll see header files, important files, and source files. In Windows, you want to right-click on source files. On Macs, I believe you use the secondary key or click and hold the mouse until the menu comes up. In the menu that comes up, select New, then Assembly File ASM. This is going to be your assembly code, your program or instructions. Now you need to give it a name and where to save it. By default, it should say it's creating it in your folder, listed here under Created File. You can leave it as the default if you want, or give it a custom name like Blinker1 or whatever you would like. When you're done, click on Finish. Notice now that the upper right-hand window turns into a text box in which you can type your program. It has a tab labeled ASM source or assembler source. This is your assembler code program source. You can type your program in here manually, only in our case we're going to cheat. I've already written the code for you and it's available in the downloads section. You can copy it all and paste that into the window if you'd like. Or if you prefer to manually type it in, that's fine too. But notice the spacing I've got here. This is the only line that should not be indented. All others need to be indented at least one space. So once you've got your source code in there, there is some settings we need to change to make sure everything is going to work. Come over here and right-click on your project name. Then select Properties way down the list at the bottom. This brings up this window. In the left pane, click on PIC 3. The properties for the PIC 3 come up in the right-hand window. Now there's actually a drop-down menu by option categories. Click on the drop-down and select Program Options. Under there, you will see this checkbox for Enable Low Voltage Programming. make sure it is checked. And again, we'll explain why later in glorious detail. Then click on the Option Categories drop-down menu again and select Power. Check the box next to Power Target Circuit from PIC 3 and change the voltage to 4.5 volts. If you do not have a voltage option as high as 4.5 volts, just select whatever the highest voltage available is. This is actually a limitation of your USB port, so it depends on the type of computer you have. My desktop computer has special high current USB ports, but I found I was still getting errors during programming. By reducing the voltage load on the USB port, I got rid of a lot of problems. So we'll select that programming voltage to a maximum of 4.5 volts. Over on the left-hand side, click on MPASM Global Options, which will bring up the compiler's options in the right-hand pane. You'll see this checkbox for Build in Absolute Mode. Make sure that checkbox is checked. After you've done all this, click on Apply down at the bottom, and then OK. Now everything should be set up and ready to go. So take a look at the assembly code. Notice that it's not all numbers like I showed you. This is assembly language, and in fact I can replace all of these commands with numbers. But this language makes it a little simpler to program because, as you'll see, it's in quasi-English. For instance, line 9 is a command to select a bank. Bank cell, short for bank select. We're going to select the bank of registers which contains the register called TRIS-C for Tri-State Register Port C. So this is easier for us humans to read, but we need to compile it into actual machine code. The compiler is one of the many subprograms included in MPLab, and that's a good name for the interface. It is a laboratory on your computer. So the compiler takes your easier-to-read quasi-English assembly code and converts it into the machine code that the PIC understands, all numbers. To run the compiler, we use the Build button, which is the hammer up top. So go ahead and click on the hammer, and you'll get a bunch of output down here in the output window. If all goes well and you did everything right, then it should say Build Successful. If you got errors here, we'll come back to troubleshooting. So assuming that the build was successful, that means it successfully converted your code into machine code. You can even look at the machine code yourself. Click on the Window menu up top, then select PIC Memory Views and Program Memory. Here you can see the codes we used called mnemonics. That has a silent M at the beginning of the word. Mnemonics are simply words symbolizing a command. So for instance, you should have a line like my line 4 here. The mnemonic was move, MOVLW 0xFF, which is a move a literal number into the working register, move LW. The number that follows, in this case, FF, is the number that will get pushed onto the working arithmetic register, which on the PICs is called the working register. So if you look to the left of the mnemonic, you'll see the actual code, the actual machine code for loading up the working register with FF. It's 30FF. 30 is the machine code, the address, if you will, for the circuitry that loads the next two nibbles into the working register. FF is what we want the circuit to load into the working register for us. So you can experiment around a little bit here if you want. In your assembly load, in your assembly code, change the number of quotes, change the number in the quotes to something other than some other hexadecimal number like AE or 08 or whatever you want. I'll change it to AE. If I build it again so that it recompiles the machine code, I look again at the program memory and notice that the same line has now changed. The 30 is still there because that's the machine code command to load the working register. The address of the circuitry, which then loads the next two hexadecimal numbers into the working register. In this case, you'll notice that the last two digits have changed to whatever you change them to. In my case, AE. If you were programming in raw machine code, the numbers, that command to move a literal number into the working register is probably the command you would use the most. So it wouldn't take long before you start thinking in machine code. You'd have it memorized that to program a line, you'd simply enter 30, followed by whatever you wanted loaded into the working register. Boom. You've just programmed a line of raw machine code. Now, I won't focus on the raw machine code here because there's some other funny things going on there. But I wanted you to see a little bit for yourself some of the inner workings of the microprocessor and how it functions. We're going to focus on programming in mnemonics because it makes things simpler. So now that you've built your code, we need to program the machine with our machine code. So make sure that you've changed those letters back to FF. Whatever you change that line in your line here, make sure you've changed that back. Now you're going to make sure that the battery power is either turned off or removed from the breadboard. The PIC is plugged into your USB port. And then click on this button here, which is Make and Program Device Main Project. That's fancy speak for program the chip already. Now, when you click on it, if you get a pop-up window like this, then just click on this line here, which is actually your PIC, and then click on OK. You'll get a bunch of notifications in the output window, and then hopefully it'll say device erased. Your status and active lights on your PIC should also flash as it's programming the chip. And then finally, it should say in your output window, programming verify complete. You have now programmed your PIC. You can now hook up or turn on the power on your circuit. The LED on your 555 should be flashing at a pretty good pace, and the LED hooked up to RC3 output on your PIC should be flashing on and off at a greatly reduced pace. In the next lesson, we'll deconstruct what we've done here and what's happening here.